In this lesson, we're going to put everything together by modeling combining functions. So usually we give a performance task on this. So we give you a function f of x, and we give you a function g of x, and then we give you a graph. That is a function which is created by combining f and g. Now, unfortunately, you don't know what or how we combine the two functions. It could be any of the ways which we've learned in this unit. And then you will say whether it's, let's say you believe it's a difference of f and g, and you will provide rationale why you believe that is the case. So I will say it does take a little bit of practice, so try to take your time and look at the graphs yourself in this handout and try to do the questions yourself, and hopefully your answers and your explanation matches with mine. Okay, so in this case, f of x is equal to 3 log x, and g of x is equal to x squared minus 4. So I've given you the two graphs, okay, color-coded, beautiful. And using g and f, I'm going to combine these two functions and create functions like this, a of x. So your job is to tell me, how did I combine f and g to create a of x? Now in the beginning, it's a little tricky because you're running through a lot of different combinations or possibilities in your head. But if you narrow it down, it's actually not that bad. Okay, so let's think about it. How can we create a of x using f and g? So let's go over the ways. So you could do f plus g. You can do well, you can say g plus f, but then f plus g and g plus f will give you the same function. So I won't write g plus f. You can do f minus g. You can do g minus f. Now, f minus g and g minus f will definitely be different. Well, most likely be different. They can be the same, but most likely different. We can do f times g. We can do g times f, which is the same as f times g. F over g. And I'm going to space g over f, and then you can do f of g. I'll just write f of g of x, and you can do, let's just do circle notation. You can do f circle g, which is f of g, or you can do g circle f. Like we said earlier, f circle g is very different from g circle f. Now it could be the same, but most likely they are not the same. So that's it. Those are the ways you can combine f and g in this unit that we've covered. So those are the different ways. So let's go back to our question now. How did we create this function a of x? What did we do? So take a look at the properties of this function. Okay, so go over, I believe there are 4 examples in this handout. So take your time, do all 4, and then continue watching this video. Okay, so hopefully you know that a of x is equal to f of x minus g of x. So that part is actually the easy part, to be honest with you. So a of x is equal to f of x minus g of x. The hard part is providing reasons or rationale why you are 100% sure that a of x must be equal to f of x minus g of x. For example, it can't be f of x times g of x. It can't be f of g of x. How do we know? So we're going to provide some just really brief, succinct points to prove that a of x is indeed created by taking f and subtracting by g. So here are my bullet points. Yours could be different. So I'm going to write a of x equals 0 when f of x equals g of x. Okay, this point helps prove to me why a of x is equal to f of x minus g of x, because when f and g are equal, a of x is equal to 0. So let's take a look. So where they intersect is about when x is slightly after 2, and guess what? That's when the function is equal to 0. And there's actually another point of intersection right about here, slightly greater than 0. And guess what? There's another x-intercept there. Okay, so that's one reason. Now, is that conclusive? Does that nail it in the coffin? And that's actually not the case right now. So a of x could actually be, based on this point I've made, can still be g of x minus f of x. Which this point is true if a of x is g of x minus f of x. So this point is not conclusive. Okay, I need to provide 3 points that leaves there's no doubt, leaves no doubt that a of x is definitely created by f of x minus g of x. If I've just left it at this point, I'm still not certain. A of x could technically still be g of x minus f of x. But I'm going to add, I have 3 points, okay? I need to be conclusive after 3 points. I got 3 bullets in the chamber. So my second point I'm going to write as x approaches infinity. Okay, I'm talking about end behavior now. A of x approaches negative infinity. So this basically removes the fact that basically tells me that a of x cannot be g of x minus f of x. Okay, because if it was g of x minus f of x, it would be going towards positive infinity. A of x would approach positive infinity. Now, since it's approaching negative infinity, I know it must be f minus g. So I don't really need a third point as of now. Okay, with these 2 points, I've basically confirmed, okay, with these 2 properties of a of x, I've basically confirmed that there was no other combination of f and g, okay, no other way to combine those 2 functions to have those 2 properties at the same time, okay? It had to be f minus g. So I'm basically done, okay? But since they want 3 points, I'll give them one more reason. Let's just talk about domain. The domain of a of x is equal to any value greater than 0. That's what the graph says. Okay, that first supports the fact that a of x is f of x minus g of x. Now, a student might come to me and say, hey, why don't we just start off with domain? Would that be a good point to make to begin with? And my argument would be no, because if you start off with that point, there are actually many ways of combining f and g that will have this domain. For example, if I added f and g, this would be the domain. If I subtracted f and g, I would have this domain. If I multiplied f and g, I would have this domain. So because of that, it doesn't really narrow it down, okay? You want to write down points or things that support your argument, that make sure that a of x is indeed f of x minus g of x, and there's no other possibility. So when you are fortunate, you'll be able to just write one bullet and you will be conclusive. But this question, I needed 2 bullets to be conclusive and say a of x is most certainly f of x minus g of x based on what I've written. All right, let's try. So if the first one wasn't good, just take a break and try to do b of x yourself. Okay, so take a look at b of x, take a look at the properties of b of x, and try to think, how did we create b of x? How did you combine f and g to create b of x? So, based on what I see, b of x is equal to f of x over g of x. So, personally, I believe that's the easy part to the question. How do I support my argument? How do I make sure that b of x is most certainly created by taking f and dividing by g? Well, the point I'm going to use is the domain. The domain of this function, by looking at the graph, is values of x which is greater than 0 and x can't be 2. Okay, so I believe this bullet point is actually conclusive. This verifies that b of x is most definitely f of x over g of x. Now, why would I say that? Because I'm running through the different combinations in my head. Okay, now it's a little tricky to do that, but with practice, you'll be getting better at it. So I'm thinking of adding f and g, subtracting f and g. That will not have this domain. I'm thinking multiplying. Nope, doesn't have this domain. Dividing. So this one's tricky. Dividing. If I divide g by f, I will not get this domain. If I divide g by f, I will not get this domain. I will get x is greater than 0 and x cannot be 1 because f of x is equal to 0 when x equals 1. What about nesting? What if I nest f of g? I don't want to spoil it, but f of g is not going to have this domain. You can write it down. In fact, you can write f of g of x because you know what f and g is. And g of f, you can develop that algebraic model, and the domain will also not be what I've written here. So in fact, based on all the different ways of combining f and g, the only way to get this domain is if you divide f by g. So I'm done. This is the only point I need to make, and that makes me certain that this graph is created by taking f and dividing by g. So since I am already sure I'm correct, I'm just going to write 2 more points to support, but I am very happy with this first point that I've made. So as x, I'm going to talk about end behavior again. As x approaches 0, b of x approaches, let's look at the graph, 0 from above. All right, what else? Let's say there's a vertical asymptote at x equal 2. And I'm pretty certain that this point is also conclusive. If the function only has one vertical asymptote at x equals 2, it must be f over g. Okay, if you were to use Desmos or some graphing software to graph all the different combinations of f and g, there's only one graph with a vertical asymptote at x equal 2. Okay, now there might be another graph that has a vertical asymptote at x equal 2, but it'll have another vertical asymptote somewhere else. So if it only has one vertical asymptote at x equals 2, it will be f over g. And like I said before, it just takes practice. You're just playing with the different ways of combining f and g, and really there's not that many. There are just 8, right? There are just 8 combinations. All right, so let's look at c of x. So take your time, look at the graph, look at the key properties, and that will help you determine how we combined f and g. Okay, so hopefully you say that c of x is f of x times g of x. C of x was created by multiplying f and g. Now, the hard part is supporting it with your points and making sure that after you've written down your 3 points, it leaves no doubt that c of x could be created using another way, or using another combination of f and g. So, I believe this first point will make it conclusive. C of x has 2 x-intercepts, one at 1 and the other at 2. And I'm just playing with the other combinations of f and g in my head, and there are no other graphs that have this property. Okay, if you want an x-intercept at 1 and 2, the only way to do so is if you combine f and g through multiplication. So, well, 1 point and I'm done. What would have been a poor point to write to begin with? The domain of c of x. The domain of c of x. Okay, if you start with domain of c of x, that wouldn't have been the best idea. Okay, because that leaves you far from being conclusive. There are 4 ways of combining f and g that gives you this domain. Sorry, in fact there are 5. Adding two differences, a product, and one way of one composite function. So there 5 of 8 has this domain. So I would argue if you're not conclusive after the first point, please, this is not a good argument to write. But I'm writing this because I'm already conclusive after the first point that I've made. Okay, so I'm gonna do one more point, but I'm already happy with what I have right here. Let's see, what does this graph have? Let's talk about end behavior again. As x approaches infinity, c of x approaches infinity. Okay, but this point is also not conclusive because what other function has that? If I add f and g, I will get this. I will get the same thing here. Okay, so I would not lead off with this. I want something that is exclusive to that way of combining f and g. This point is exclusive, okay? But sometimes it does take 2 points, so that's why we give you 3 opportunities to narrow it down and be certain that what you said is correct. Okay, last one, d of x. Take your time, look at d of x. How did we combine f and g to create d of x? Okay, so this is the easy part. D of x is actually, let's see, it's a composite function, so be careful. How did we nest it? It was f of g. Okay, it was f of g of x. Because you'll get 3 log of x squared minus 4, and that's why you see this symmetry effect. You see the 2 vertical asymptotes as well. So look at the graph. What's the property that exists in this graph for d of x that will basically ensure that you create a d of x by combining f and g using this composition? So the property that I'm looking at, you might have something different, is their vertical asymptotes. X equals 2 and x equals -2. No other way of combining f and g will give me these 2 vertical asymptotes. Okay, so basically after I've written this down, after I've said that there are 2 vertical asymptotes, I'm certain it has to be f of g of x to create d of x. There's no other way. Actually, this one's actually very nice. There's a lot of single points I could make that will just tell you for sure that it's f of g of x. Something else you could have written is the domain. The domain of d of x is less than -2 or x is greater than 2. What else could you have written? You could have written the function has line, or the graph of the function has line symmetry about y-axis. No function, okay, no other function that I create using f and g will have line symmetry about the y-axis. And same could be said for the domain, same could be said for the vertical asymptote. So all 3 points that I've made is exclusive for d of x. Okay, so just by writing any one of these points, I am certain that d of x is equal to f of g of x. Okay, there's no other way of combining f and g to create any of these properties. So I'd argue, even though the graph of d of x looks pretty funky, it's one of the easier graphs to prove how you combined f and g. So I know this lesson is a little tricky to begin with because you have to play with the different combinations in your head. But if you're really struggling, my hint to you is instead of writing f plus g, f minus, just write out the algebraic model. Like instead of saying f plus g, write down 3 log x plus x squared minus 4. Okay, and then so forth and so on. By writing out the equation, I believe it's easier to match it up with the properties you see in the graph. Okay, hopefully that wasn't too bad.